You're reading this sentence right now, this moment, this exact instant. But here's what's going to mess with your head. By the time your brain processes these words, by the time you understand what I'm saying, this moment is already gone. It's in the past. You're always living in the past. Always. And you don't even know it. Most people think they know what time is. It flows forward. Past, present, future, 1 second per second. Tick, 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 like a river carrying us along. But that's not what time is. That's not even close. Time is so much stranger, so much more slippery than you think that once you see what's really going on, you'll never look at a clock the same way again. Let me show you what I mean. Here's a simple experiment. Clap your hands just once. Sharp clap. When did that happen? When did the clap occur? You think that's an easy question? Just now. It happened just now. But what is now? When exactly was now? Your hands touched. Sound waves traveled to your ears. Your brain processed the sound. Which moment was the clap? The moment your hands touched. The moment the sound reached your ears. The moment your brain said, I heard a clap. They're all different moments, different nows. So when was the clap? This isn't word games. This is the fundamental problem of time. There is no universal now, no cosmic moment that happens everywhere at once. No shared present that everyone experiences together. Einstein figured this out, and it breaks everything you think you know about when things happen. Let me tell you about something that happened to me years ago. I was at a party standing next to a physicist from CERN, smart guy. We were talking about particle accelerators. He mentioned that particles in their experiments live for incredibly short times, microseconds, billionths of seconds. Then they decay. But here's the weird part. They could track these particles, watch them travel across their detector before decaying. The particles were covering distances much farther than they should be able to travel in their short lifetimes. According to our clocks, they should die long before reaching the other side, but they don't. They make it. I asked him, how is that possible? He smiled and said, time dilation. The particles are moving so fast that time slows down for them. They live longer than they should. But then I realized something. He was wrong. Not about the physics. The physics was right. He was wrong about the explanation. See, he said time slows down for them. But that's thinking about it backwards. From the particle's perspective, time isn't slowing down. From the particle's perspective, its lifetime is exactly what it should be. Normal. It's our time that's different. The particle lives its normal lifespan and covers its normal distance. But to us, watching from our reference frame, it appears to live longer and travel farther. There's no absolute clock, no universal timer. Time depends on who's measuring it. My time, your time, the particle's time. They're all different. They're all equally real. And none of them is more correct than the others. This should break your brain. We're not talking about perception. We're not talking about psychology. We're talking about the actual passage of time being different for different observers. If you're moving fast relative to me, your clocks literally run slower than mine. Not because they're broken, because time itself passes more slowly for you. Let me make this concrete. You have an identical twin. Your twin gets on a spaceship and travels to a nearby star at 90% the speed of light. The trip takes, let's say, 10 years by your Earth clocks. Round trip, 20 years. When your twin comes back, you've aged 20 years. Your twin has aged only about 9 years. Your twin is now 11 years younger than you. This isn't science fiction. This is tested physics. We've done this experiment with atomic clocks on airplanes. The moving clocks run slow, exactly as predicted. But here's what really gets me. From your twin's perspective, the trip didn't take 20 years. It took 9 years. And that's not because your twin was mistaken or confused. Time actually passed more slowly. 9 years is the correct time for that trip from your twin's perspective. 20 years is the correct time from your perspective. Both are right. Both are real. Time is not universal. Time is personal. Every observer has their own time, their own rate of aging, their own version of now, and it gets worse. Gravity affects time too. The stronger the gravity, the slower time passes. If you're standing on the surface of a neutron star, time moves noticeably slower than it does here on Earth. Your watch would tick slowly compared to a watch floating in empty space far from any massive object. This isn't theory. GPS satellites have to correct for this. They're farther from Earth's gravity, so time passes slightly faster for them. If we didn't account for this, GPS would be off by miles. So what is time? Here's what I think time really is. Time is what prevents everything from happening at once. That's it. Time is a dimension, like the 3 dimensions of space. But unlike space, you can only move through time in one direction. Forward, always forward. And the rate at which you move through time depends on how fast you're moving through space and how deep you are in a gravitational field. Think about it this way. You're always moving through space-time at the speed of light, always. But that motion is divided between space and time. If you're sitting still, all your motion is through time. You're moving into the future at maximum speed. But if you start moving through space, you have to divert some of that motion away from time. You're now moving through space and time, which means you're moving through time more slowly. The faster you move through space, the slower you move through time, and there's a limit. If you could move through space at the speed of light, you would have zero motion left for time. Time would stop for you. This is why time doesn't pass for a photon. From a photon's perspective, it's emitted and absorbed in the same instant. Now here's the deepest question. Why does time have a direction? Why do we remember the past but not the future? Why does cause come before effect? Why can't we go backwards? The answer isn't what you think. It's not because of some fundamental law of physics that prevents time travel. There's nothing in Einstein's equations that forbids going backwards in time. The answer is thermodynamics. Entropy, the tendency of systems to become more disordered over time. Imagine you're watching a movie of an egg falling and shattering on the floor. Normal, right? Now imagine running that movie backwards. You see the scattered pieces of eggshell suddenly jump together, forming a perfect egg that leaps up into your hand. You know immediately that you're watching the movie backwards. But why? What law of physics is being violated? None. Every individual molecular collision in the reverse movie follows the laws of physics perfectly. What gives it away is probability. It's not impossible for the shattered pieces to spontaneously reassemble into an egg. It's just incredibly, ridiculously unlikely. So unlikely that it effectively never happens. That's the arrow of time. Things tend to become more disordered, more spread out, more mixed up. Not because they have to, but because there are vastly more ways to be disordered than to be ordered. You can scramble an egg, but you can't unscramble it. Not because it's physically impossible, but because it's probabilistically impossible. We remember the past because our brains are physical systems that record information. Memory formation increases entropy. It creates disorder in the form of heat. So memory formation is directional. It only works forward in time, from low entropy to high entropy. The universe started in an incredibly ordered state, low entropy, the Big Bang. Since then, entropy has been increasing. Things have been becoming more disordered, and that increase in entropy is what gives time its direction. The past is the direction of lower entropy. The future is the direction of higher entropy. So here's what time really is. Time is the dimension along which entropy increases. Time is what allows change to happen. Time is what makes cause and effect possible. Without time, everything would be frozen. Nothing could happen. Nothing could change. Nothing could exist. But time is also personal. Your time, my time, they're different. They run at different rates. The faster you move, the deeper in gravity you are, the slower your time compared to someone else's. There's no universal clock ticking away somewhere. No master timekeeper. Just billions of personal clocks, all running at slightly different rates. And here's the beautiful part. We figured this out. Humans sitting on a small planet, using nothing but our brains and some careful experiments, figured out that time is relative. That time is a dimension. That time has a direction because of entropy. We discovered that the thing we experience most directly, the passage of time, is actually one of the most profound mysteries of the universe. Every second that passes is a second that will never come again. Not because time moves forward, but because entropy increases. The universe is becoming more disordered, more spread out, more mixed up, and that process is irreversible. You can't go back. You can't undo the mixing. You can't decrease the total entropy of the universe. So when you look at a clock, remember what you're really seeing. You're seeing entropy increase. You're seeing the universe become more disordered, one tick at a time. You're watching time itself, the dimension that makes change possible, the thing that separates cause from effect, the personal, relative, flexible thing that Einstein showed us is far stranger than we ever imagined. That's what time is. Not a river, not a clock, a dimension of reality that you move through at your own personal rate, always forward, toward higher entropy, toward a more disordered future. And the fact that we can understand this, measure it, test it, predict it, that's what makes physics beautiful. We live inside time, but we can step outside our intuitions about time and see it for what it really is. That's the power of careful thinking. That's the beauty of physics. Time isn't what you think it is, but now you know what it actually is. And that's more beautiful than any simple answer could ever be.